Okay, so the next lesson here is really a short and fairly simple one. We're just going to prove two very basic theorems about graphs. Both are I'm going to call both of them lemmas, I suppose. They're really I guess in the notes one is a lemma, one's a theorem. Anyway, they're both very simple properties, and they both involve just a nice choice. So our first lemma is the following: if every vertex of G has degree at least 2, then G contains a cycle. This is a very easy lemma that can be proved a number of ways. One thing you can do is just sort of start greedily constructing a walk. But since I spent some time emphasizing it, let me suggest an alternate proof. Let's choose a maximal path. Once again, I'm looking for a cycle in the graph. Let's just a path is path plus an edge would give you a cycle. So let's choose a path, and let's choose one that's maximal. The nice thing about maximal path is that it always exists. So let's choose a maximal path P of G, and let me call the ends of P x and y. So let's let x comma y be the ends of P. Right? So okay, so I'll draw a picture. There's x, there's y, here's my path P. Of course, this exists as a subgraph of our larger graph. And what would I like to do now? Well, I want to look at those two vertices, x and y. And now, as we discussed in the problem session earlier this week, there's a nice feature that the ends of your maximal path have. So here my ends are x and y. And what does it mean for my path to be maximal? Well, I can't extend the path by adding another vertex and an edge between that vertex and x, right? So another way of saying that is every vertex in my whole graph G that's adjacent to x must lie on this path P. And the same must be true of y. So let me just make that. This is really a key property. This is the key feature of a maximal path. So let me just note. So we'll note that all neighbors, that means a vertex adjacent to, neighbors of x and y lie on P. Again, this is an immediate consequence of the fact that our path is maximal. Because you can't take this path and grow it at this end, well, that means that there's no neighbor of y that's not already on the path. And same thing, because you can't grow it at this end, there's no neighbor of x that isn't already on our path. Okay, and now we're pretty much done. So x only has degree 1 within this subgraph P. It therefore has to have another edge incident with it. Let's consider that edge. The other end of that edge must lie on this path P, and that gives us a cycle. I'm not going to write that much of it. I mean, there's another proof of this in the notes. This is very straightforward. I'll just say, since the degree of x is bigger than 1, I can choose an edge incident with P. Incident with x that's not in P. I can choose an edge E. This is an edge of G, but not an edge of P, incident to x. And now I'll just say quickly, now the graph that you get by taking our path P and all plus this new edge E, that subgraph is going to contain a cycle. there's a cycle. There's a cycle using. Let me just say with edge set. A subset of the edges of the path together with this new edge E I found. So in terms of our original picture that I've drawn here, there's some other edge E. There it is. I don't know, E could be a parallel edge or even a loop. I don't really care. The main feature of E is that it has X as one of its ends, and its other end is also on the path. So all of its ends lie on this path P. So if it's a loop at X, fine. That loop itself is already a cycle. If it was a edge in parallel with that first edge in the path, no problem. That's a cycle too. Whatever you want to do. This edge E, it has it's going to form a cycle with P, and that's our proof. Okay. So let's do one more. I guess this one's called a theorem in the notes, so I'll call it a theorem too. So the statement is that every loopless graph has a bipartite subgraph that contains at least half of its edges. So every loopless graph G has a bipartite subgraph. H with the property that H has at least half the edges of G. So the number of edges of H is at least 1/2 of the total number of edges of the graph G. Okay. Now what we're going to do is prove this. And again, what we're going to do is kind of make a greedy choice. Now, you know what a bipartite subgraph is, right? If you're looking at a bipartite subgraph of G, that bipartite subgraph has a bipartition, right? So, I mean, you can think of that as it's a partition of the original vertex set of G into two sets, A and B. And when you form your bipartite graph, you might as well take all of the edges going in between. You wouldn't have to, right? Of course, if I've made a bipartite subgraph H, I could delete an edge from that, and I'd still have a bipartite subgraph. But we're trying to find a bipartite subgraph with as many edges as possible, right? We're trying to prove that there's one containing at least half. So when we're thinking about selecting that bipartite subgraph, I really may as well select just the two sets A and B that are going to be forming the bipartition, right? So what we're really trying to do, in other words, is choose a pair of sets, A and B, pair of disjoint subsets with union equal to the whole vertex set, so that the number of edges going between A and B is at least half of the total number of edges in the graph. Okay. Now, what we're going to do here is we are just going to go in a greedy fashion. I'm just going to choose this pair of sets A and B so that I maximize the number of edges in between them. So again, what I'm going to do is I'm going to choose subsets A, B, subsets of V of G, such that, well, A and B have to be disjoint, and their union should be the whole vertex set. But what I want to do subject to that is I want to maximize the number of edges with one end in A and one end in B, so that the number of edges, I'll just say A to B, is maximum. So I want to prove I want to prove that there's some bipartite subgraph that has the feature that it contains at least half as many edges as G does. You know what that bipartite subgraph may as well look like. I'm just taking two sets A and B, partitioning the vertices into A and B, and I want to show that I can choose that A and B so that at least half the edges go from A to B. And we're just going greedy. We'll say, okay, let's take the best one we can find. Let's choose this partition of our vertex set into A and B so that we maximize the number of edges with one end in A and the other end in B. Okay, and now what we're going to do is we're just going to investigate what happens at a single vertex. But it'll be helpful just to go ahead and well, let me draw a picture. So here's our set A. Here's our set B. And what I want to do is I want to consider a vertex and think about where the incident edges are. Okay, so let's think about a vertex over here in A. Let's call it V. And let's think about of the edges incident with V. They now come in two types. There are some that have both ends in A and some that have both ends in B. So I'm just going to say let V be in A. In fact, let me say this a little differently. Let V be a vertex and assume without loss of generality that V is in A. I could switch the identity of A and B here and it wouldn't change my choice, so I can assume without loss that this vertex V is in A. That doesn't really change anything. So I've taken my vertex V, and now I want to think about the different types of edges that are incident with this vertex V. Now, as I said, they come in two types here. Let's suppose there are S edges here and T edges here. So let's suppose let S equal the number of edges incident to V with both ends, in A, and I'll let T be the number of edges incident to V that have one end in B. Of course, the other end will have to be in A because the vertex V is already in A, and by assumption, this edge is incident with V. Okay, so we have, so we're picking on our little vertex V. What we're seeing is that V has S edges that join it to other vertices in the set A, and has T edges to the other side, right? And now, what can we do? Well, we could consider the effect of taking our vertex V and moving it out of A and moving it into B, right? That's a thing we could try to do. I could take my vertex V and say, hey, could anything get better if I moved you to the other side, right? And what is going to happen here if you move V to the other side? Well, when we move V into, when I take it out of the set A and move it into the set B, all of a sudden those T edges that were joining V to the other side, suddenly those are no longer going to be in our bipartite subgraph, right? Those are no longer going to be going between the two sets, but those S edges that were joining V to other vertices in A, those will be going between our new A and our new B, right? So again, what we've done here, we are looking to find a bipartite subgraph with at least half the edges. And what we've done is we've just gone greedy. We've said, hey, give us the bipartite subgraph with as many edges as possible. And that's all well and good, but you have to be able to sort of take advantage of that fact. You have to be able to, maybe that has enough edges, maybe it doesn't, but you have to prove something. And so in order to prove something, we have to consider trying to take this choice that's supposed to be the best and modify it, right? And what we're doing here is we're recognizing that if you take the vertex V and send it to the other side, we can tell the effect of that on the number of edges between A and B, right? Because our pair AB was chosen to maximize the number of edges between A and B, I know that in this case T is going to be greater than or equal to S. If S was bigger than T, I'll just write this here. So if S was bigger than T, moving V to B would contradict our choice, would give us a new pair of sets A and B that would just have more edges going in between them. And we chose our AB so that was maximized, so that can't happen. So if S was bigger than T, then moving V to B is contradicting our choice. So that means that T is going to be greater than or equal to V. Now, let me show you how we'll take advantage of that. Let's define H to be the subgraph of G given by all the vertices and all of the edges between A and B. So this is the bipartite subgraph of G with all vertices and just the AB edges. Oops, that was not so smooth. Yeah, I'm gonna just leave that as it is. So I'll say that in words because I can't click that with my pen. Again, I'm declaring H to be the bipartite subgraph now. It's going to contain all the vertices of the original graph and just those edges from A to B. And I'm claiming here that, in fact, H is going to be good. And what's the key feature here? Let me just jump to the next page. Well, no, I'll write it. Maybe I can get it all in here. So the key feature here, which is coming from this point, what I know is that the degree of in the subgraph H of V is going to be at least half of the degree in the original graph G of V, right? So for every vertex V, when you look at its degree in H, that means the number of edges that go from A to B that are incident with it, that is always greater than or equal to the number of edges within its same set, within its same block that are incident with that. So what that means is that the degree of that vertex V in the subgraph H is at least half of the degree of V in the original graph, right? And that's the equation that I've just written here. So this is the key feature we have, and this is going to be true for every vertex V, right? So again, for every vertex V, its degree in our subgraph H is going to be at least half of its degree in the original graph, and this is all that we need to complete the proof. So now you remember that twice the number of edges of H, this is equal to the sum over all vertices of the degree of the vertex. But again, when I'm adding up the degrees of the vertices in H, those are always at least half of the degree in G. So this is always greater than or equal to 1/2 of the sum of the degree in the original graph G of V. Right, that's at least half of the degree of the vertex V in the original graph. But when you sum up the degrees in the original graph, you get twice the number of edges in the original graph. So this is equal to, so that 2 cancels with that 1/2. So this is equal to the number of edges of G. So you can see that completes our proof. So now I've learned that twice the number of edges of H is at least the number of edges of G, and that's what I needed to prove. So in other words, my graph H has at least half of the edges of the original graph. This is a very nice proof technique. Sort of very nice when it works. Let me emphasize the thing that goes on here again. We're looking to find a subgraph with a certain property. What we've done is we've just chosen, in some sense, the best one we can find. And that's a great start. But if you're going to make some actual use out of it being the best one that exists, you're going to have to consider making some movements to see why you can't get a better one, right? You're going to have to take advantage of that fact that you can't get a better one. And in this case, what we're doing is we're doing that very locally. We're just sort of looking at each vertex and saying, well, what would happen if I moved you to the other side? Well, if I move you to the other side, the edges that join you to other vertices in the same block, those suddenly count for me. Those would be contributing. And those edges that join you to the other side don't. So that tells me that for every vertex V, the number of edges joining it to the other side has got to be greater than or equal to the number of edges joining it to vertices on the same side. And that tells me that the degree in that bipartite graph that I form with the edges between A and V, the degrees in that graph are always at least half of the degrees in the original graph. And there you go. That means that my subgraph H is going to have at least half the edges of G. Okay, so that'll complete it for this little lesson.